Okie dokie, friends. Let's start. Welcome, everybody, to our first classical mechanics lecture. Very excited. Somehow we have a small quorum of in-person people today, but we'll make it work. I have a very fun activity that is going to feel like Monopoly, like we're playing Monopoly, but it's going to be with energy bills. So before we start, I actually saw somebody joining us online for the first time. Casey, do you want to say hi and introduce yourself?
Sorry, I don't have video right now, but
That's okay. We hear you.
Casey. I'll be joining in the fall.
Hmm?
I don't know what else.
Where are you right now?
Oh, I'm currently in New Mexico.
Hmm?
Uh,
Probably having a better temperature than we do. It's very hot in here.
it's also extremely hot here, but maybe in the 80s or something.
Okay, no, we were near the hundreds
Oh,
yesterday. Yep.
I'm very sorry.
I am very sorry too. It's really, really bad. When are you joining us in person?
Um, uh, Maybe, probably I can't make it until August, so I don't know
Okay.
if this course will still be going on then, but
Maybe, but that's okay. I am very glad that you can join us remotely. You have been able to follow us through the videos, right?
yes.
Excellent. I am behind, per usual, on everything, but in particular with the last two videos from last class. I am going to be working on that this week, but if you want to watch them earlier, let me know and I can give you access to the folder where I have the raw recordings.
Sounds good. Thank
Excellent.
you.
Of course, of course. Final question, do you mind being recorded? I need to ask that
Sure.
to everybody. Excellent, very good. Okay, so we can officially start. Remember to be nice to each other and to yourselves. This is the usual slide with the resources that you can check to follow all the things that we're doing. And last week we finished math. We went through many topics and we closed with rushing complex numbers, which I realized that was maybe not a great idea because we are definitely going to need complex numbers for quantum mechanics. So on Wednesday, I'm going to be talking about representation and Ketz and Brass. Let's talk about complex numbers once again, just for a little bit. I think that will be useful. Just remind me that I do that. But I think beyond that, it went really well. Is there any question from anybody in person or on Zoom? Any clarification, anything that you would like me to emphasize more later? Very good. So then with that, we are going to officially start with classical mechanics. The menu, I have been thinking of some things in here. I need to update this. This is a draft of what we're going to be covering. We're going to talk about the Newtonian approach today to moving things. We're going to talk about conservation of energy and where that could be useful. With that, hello, welcome. Oh, I have something for you. Hi, Cooper. Can you come and pick it up? I have for you this because you missed actually yes, so you missed the ice cream on Wednesday and this is because you found the ice cream on that one. You didn't come with ice cream with us, so this is for you so that you can go and have ice cream. And Casey, I have a voucher for you as well. Whenever you come in here, you can enjoy the ice cream and I'll give it to you. It's in here. But of course, yeah, Cooper got two because he did find that treasure on the first class. All right, so the activity for today, so full disclosure, I did try something similar like this to last class, and I kind of like it, but I didn't like it as much as how it went, so I have changed some things. This is relatively new. I have no idea. It might be that we have a blast, and you say at the end of this class, wow, now I understand conservation of energy so much more, and this was super useful. Or you leave the class thinking this was so awkward. The professor asked us to walk around exchanging money like if we were playing Monopoly. I will appreciate your feedback after to see if we can make it better. It's with my best intention. So if halfway through you will realize this is kind of boring and awkward and it's not working very well, we just focus on the math. If you're enjoying it, we're going to continue. I have 4 physical systems that we're going to play with the math, and then we're going to, for each one of them, we're going to play this game with the Monopoly money that I have in here. It was designed by ChatGPT a year ago. I didn't have time to update it, and I kind of treat it as a legacy thing. So maybe as I move forward with this class 20 years down the road, I will still be using this currency. So the idea of each one of these is to represent 1 joule of kinetic and potential energy, and we're going to see how they exchange each other. I also printed station letters. So we have 3 people in person, including with me 4. So we're going to see how we distribute these ones. So you have stations, and each one of you is going to play as a particle at some point. You're going to have to go to the stations and exchange money. The role of friction is going to be played by the IRS, and it will be tax on joules that will be collected, and you don't see them back. And we'll talk about that on the physical way, why that makes sense. Okay, so with that, let me stop sharing here. Okie dokie. So we took a look at what we have done before. This is a classical plan. We're going to talk about the Newtonian approach. As I mentioned, the energy conservation, friction. I don't know if today we're going to talk too much about rotational things, but eventually we're going to talk about that and moment of inertia, rotating things. I think very quickly, if not next class or the class after, I am going to define Lagrangian mechanics, and we're going to start looking at things through that lens, because I think that is fantastic. It adds so much more understanding to what is actually happening. It makes life so much easier. So I don't want to have to think of vectors and Newton's equations for too long. And then down the road, we're going to explore normal modes. We're going to talk about orbits and Pauli scattering. And by the end, we're going to talk about Hamilton's equations of motions and why will anybody care. And funny enough, if we do things right, the last class of classical mechanics, we could close with understanding how looking at mechanics through the Hamilton's mechanics perspective naturally leads into a Hamiltonian description of quantum mechanics, which when I was in undergrad, I was fortunate enough that that was my last class of classical mechanics. And the very next semester that started a couple of weeks after, we started with our first quantum mechanics class. You're not as fortunate because you're going to be seeing quantum mechanics and classical mechanics at the same time. So this is kind of like watching the Marvel movies out of order. So then one of the characters dies, but they haven't died in the other movie. So you will have to put a coherent story afterwards. Okay, the 4 systems that I want to study with you, we're going to throw a ball out of a building, not in real life. We're going to do that with calculations. We're going to ask questions about the time of flight, the maximum height. So that is the first system that we're going to play with. And we're going to ask questions like, what is the maximum height that the particle reaches? How much is the time of flight? And then the other system is going to be a spring that just oscillates back and forth. We're going to try to tackle some questions. We're going to have a particle that is oscillating in some sort of a cone surface that I put some friction. So every oscillation is going to take away some of the energy. We're going to try to calculate what is the maximum height that the particle comes back to after 2 oscillations. And then the final problem, a serious classical mechanics problems, we're going to be asking what is the height that I have to throw my particle from such that it can go over a loop. There is some friction, and after the particle has gone over the loop, it's going to compress a spring. And we're going to try to estimate how much is that spring compressed at the end. We're going to see if we have time to do all of this. If we don't, then that's homework for you, and you will have to do some things in there. Is the approach clear? In many of these, we're going to try to solve them using forces and Newton's equations and get differential equations. Very quickly, we are going to appreciate how much having conservation of energy and talking in terms of this monopoly money looks like. So let's start with my first situation. I have a building of height h, and I'm here with all of you. And Casey, you're on a laptop. And we're going to throw a baseball with some initial velocity v0. Let's say that this angle is 45 degrees. And then the baseball, you call it baseball or baseball ball? I guess baseball. The baseball ball is going to do an arc like this. And then it's going to hit the ground. And the two questions that I'm after, I would like to know what is the maximum height that this baseball ball gets up to, and how much is the total time that this thing is on the air. Make sense? Let's put some numbers, and I think I already put some numbers in here. I'm going to just copy them. The numbers are going to be important later for when we want a numerical answer and when we're playing with the monopolymer. How do I solve this problem? What do we do? What do I need to find? What will be a good degree of freedom to describe, hello, what is happening to this system? I'm going to put this in here so it captures the three of you better. What do you folks think?
Focus on motion x and y direction. And thinking about, like, we're trying to find the height, the maximum height. We're going to have zero velocity in the y direction.
That is true. So perhaps we can use some conservation of energy there to figure that height. For a second, because I do want to contrast the two of these. What if you didn't know that energy is conserved, or it was not straightforward to implement? What could be a good way of answering these questions? I need equation of motions. I have a constant acceleration, yes. So basically, my recommendation, the way that I would love for you to start thinking about this. Remember how I told you originally when we had the second differential equation, and the first thing that I want for your mind to come is like, oh, sines and cosines. Remember that's what I'm trying to trigger in here is not sines and cosines. What I'm trying to trigger in here is a two-step process for you. The first step is to ask degree of freedom or descriptor of the system or variables of interest, the thing that I'm after to try to understand. That is the first step. And the second step is equations for their dynamics. So almost, if not every problem that we're going to be talking about today and in general, I want your first reaction to be almost instinctively. I need to figure out what are the quantities that describe my system that I'm after, that I am interested in, and what are the equations of motions for this quantity. For example, is the color of the ball a quantity that you're interested in here? Not really. Could be any color, and it will not affect the two questions that I'm asking. So what will be good set of numbers to describe the state of my system as time progresses?
Its height would be helpful.
Its height will be helpful. Its height as a function of
time.
Excellent. Let's call that y as a function of time. H, I could call it h, but h is already a number in here. So y is a function of time, and what is the other quantity?
I guess x as a function of time.
Maybe at the end it's not necessary, but let's put it anyways, because those are, if you think about it, those are the two numbers that I need to specify any state of my system, the system of interest. With these two, I cannot know whether or not the battery that holds Casey's laptop is holding true, but that is not a degree of freedom that I need to answer the questions. Sounds silly, but it's really important to distinguish between these two things. And the reason is because later, when we have systems that we have to approximate things, that will happen whenever you go, for example, to statistical mechanics. You're going to say, I have 10 to the 24 atoms in a box, and we're going to come and say, I'm going to ignore all of these degrees of freedom, and I'm going to pick a handful of things that I'm going to be tracking, like pressure, volume, temperature, etc. That is that compression that makes you a good physicist, a good scientist, to find what are these numbers. So these two numbers, you know, I'm going to argue that this is just the position of the particle as a function of time. It's a vector. It's two numbers. But I want the next time for this to come super quickly where you say, oh, yes, obvious. What are we after? The position of the ball as a function of time. Yep. Everybody following? Casey, you following? Will you tell me and interrupt me if at some point you're not?
Yes,
Excellent.
yes, yeah.
Very good. Very happy. All right. So now I need equation of motions for these things. Where do I find an equation of motion that tells me how to obtain the position of the particle as a function of time? Don't mind me. Just put in this here.
Probably starting with force equals mass times acceleration.
So what is a Newtonian approach to dynamics? You come and you tell me, find my degrees of freedom. Have you found them? Yes. Positions, right? Yeah. Positions, velocities, accelerations. Okay. You need to figure out what are all the forces that are acting on my system. Have you figured them out yet? Well, not yet. We're going to think about them, but can you figure them out? Yes, of course I can. Okay. The equation that you're after is then that the total number of forces acting on your particle is going to be equal to the change with respect to time of the momentum of the particle. And that is your second step. That is find me dynamical equations for them. Later, when we do Lagrangians, it will not be an equation with vectors. It will be you write the Lagrangian of your system, and then you write the other Lagrange equations. And with that, you obtain the dynamical equations on how your generalized coordinates evolve with respect to time. But in this case, we're following Newton's, the apples, the planets, yada, 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 and that's what we're going to do. Make sense? Okay. What are the forces acting on my particle? Right after I release it, because before I release it, my hand is making a force, and that is complicated. Just gravity. I'm ignoring air because I want to be able to finish this calculation today. So the only force that is acting on the particle, the force in x is 0. The force in y is minus mg. And that's it. Sounds reasonable, right? Okay, let's write it down. Momentum for the particle in this case is going to be mass times its velocity, that is equal to mass times r dot. That dot means derivative. If at some point I write something that doesn't make sense to you, please interrupt me. Remember that these lectures are for you. If the mass of my baseball ball is not changing with respect to time, then the derivative of the momentum with respect to time only enters through the velocity. So I recover the equation that we all know and love, which is the force is equal to mass times the acceleration of the particle, that I'm going to write it as r dot dot as a function of time. And this further, I can separate it into two equations because this is a vector equation. A vector equation looks like fx, fy, this is equal to m times r x dot dot y dot dot. So my two equations are the forces in x acting on my particle is going to be equal to m times x dot dot. The forces in y of my particle is going to be equal to my dot dot. Is everybody happy with this until now? It's reasonable. What now? Did I solve my problem? Why not? But I have a differential equation for them, which is a level 3 problem. Maybe there is a way in where we can solve this and obtain my answer. But once that is done, in principle, you could plug this into a computer and you're done. So that is the step process that I want you to mimic. Coordinates to describe my system, equations of motions on how they change with respect to time in this case, and then the mathematical process of solving it. So help me out. How do I solve them? Can we try the first one? What are your thoughts on the first one? So objective, I'm going to put it in here. Objective, obtain x as a function of time, and obtain y as a function of time. Nope, not 0. Why I'm saying 0. So how do I obtain x?
Up the equation.
So I could integrate that. How much were the forces in x?
0.
So I have 0 is equal to mx dot dot as a function of time. So this mass goes away. I actually don't care how much is the mass of my particle. And then you could integrate. That is one way of doing it. You say, well, I integrate on both sides with respect to time. I put a dt prime in here and integrate this from a t0 to a time t. Another way of doing this is asking yourself the question, I have a function whose second derivative is 0. Sorry. Yes, let me go step by step. You can say this is x dot as a function of time, all of this dot, and this is equal to 0. So I have a function whose first derivative is equal to 0. What is that function? It's a constant, right? So that means that x dot as a function of time is a constant that, because we know that x dot has units of velocity, I'm going to call that constant v naught. We're going to put it in x. Yep. And now I have a function whose first derivative is a constant. I'm guiding you through a process that at least I find it more natural. The integration will always give you the right answer, and we're doing basically the same, but I prefer to ask myself the question, what is a function such that this happens? Especially with these ones, these are so simple that I find myself less prone to errors if I reason in this way. So I have a function whose time derivative is a constant. Casey, you want to give it a try with this one?
Sure. The velocity is whatever speed you threw it at in the x direction.
That is true, and we're going to get to that later, but right now I'm still trying to find who is x of time. We got how much is x dot, but how much is x?
I see. V times t.
So no, that's perfect. Reasoning in this way.
Dot times t.
Sorry?
Okay. Oh, sorry. Yeah, go ahead. Yeah.
You're doing great, but thinking in this way, a function whose first derivative is a constant, that must be a linear function in time. Yep.
I see.
The same as when you have two derivatives is equal to minus the function I said, sines and cosines. If you see an equation like this, the first thing that should come to mind is, a linear function. Yeah, of course. So from this one, you obtain that x as a function of time, exactly as you said, will be v0x times t. It's a linear function, but a linear function also can have a constant term. The intercept, if you were to think of this as a straight line, right? And a way of verifying that you're not doing something wrong on all of these steps is you can take the derivative of this whole thing, and you realize that the derivative of this gives you back what we want. So this is x as a function of time. This extra term may or may not be important, or may not be used later, but it's important that you put it. Yep. And you will get the same answer if you keep integrating, because integrations are defined up to constants. Still, I find this more intuitive. So that's it. We got the position of the particle in x as a function of time, and I have two constants that I can adjust to meet my needs. And the two constants are this friend and this friend. And this tells me at t equals 0, where the heck was the particle? Well, if we said that my coordinate system is such that this was x equals 0 and y equals h, my particle in x at t equals 0 was at 0. And the initial velocity, well, I got numerically, I told you how much the initial velocity as a vector was, and I told you that this was 45 degrees. So this whole number has to be equal to, how much did I say? 14.14 times the cosine of pi 4, which is 45 degrees. So this is square root of 2 over 2, 14 times 14 meters per second. Please, go ahead. You're asking why we have such weird numbers? sorting. Yeah. Yeah. That will appear later because we're going to play with the bills so that I end up with round numbers for the energy. But yeah, this is basically how we find the dynamical equation. Okay, excellent. Now, what is left for me to do in this case? Yeah. So what do I write?
In this case, it's mg.
Excellent. So the equation for y as a function of time, I have mg. The force is pointing down, right? So I better put a minus. And this should be equal to m times y dot dot as a function of time. So the m's cancel. And I have a function, let's play the same game, minus g is equal to y dot as a function of time, all of this dot. I have a function whose first derivative is a constant. What is that function? So linear. It's a linear function. So that means that y dot as a function of time is equal to a linear function in time, which is going to be minus g times t plus
V naught.
excellent. Right? Excellent. Very good. Now I have a function whose first derivative is a linear function. What do you think is going to be the function? Right? So if I put minus g t squared, by the way that you check this is if you take the derivative of what we wrote on the right-hand side, gives you what we were looking at. Checking whether or not you solve a differential equation is usually very easy to check if the solution is the actual solution. So what happens if I put a g t squared in there? When I take the derivative with respect to time, I will recover this gt, but I will get a 2 that I don't want. I'm going to divide by 2. Such that when I take the derivative, yeah. What about this term? What do I get with that one? Very good. And am I missing anything? What am I missing? And to check on your creativity, how should we name this constant? Very good. And the role of that y naught is to tell you at t equals 0, where was the particle? Sorry? Right? Where in y? And in this case, where in y? Well, we said it was a height h, which is the height of the building, which I don't remember what I put. Height 10 meters. How much is v naught y? The same as v naught x. That is 14.14 times the square root of 2 over 2 meters per second. And g is 10 because I'm lazy. And that's it. You have not completely solved the problem because the problem was asking you for specific numbers, but you have solved 99% of the problem because you now have access to the degrees of freedom, the coordinates that describe your system as a function of time for every time. Any question that anybody wants to ask to you, what was the position of the particle when t was, you can answer. Yeah? Now we're going to go and answer the 2 questions. So once I have that, how can I find the maximum height that the particle has? So basically, particle is thrown, does this, and then hits the ground. How do I find this location? What do you think? Why?
Because that's the point where it's maximum. So right when it hits there, it's instantly rate of change zero. Basically, it represents the maximum.
That we already know. We found it on the way.
True.
Well,
Using the velocity that we found along the way.
I didn't think of that. That's brilliant. We already have, yes, it's the same process, but why take a derivative when we already know the velocity as a function of time? So you just ask when is this equal to 0. I love it. Thank you, Alex. The one caution that I wanted to give you is that this whole trajectory looks like a parabola, but y is y and x is x, but this is not y as a function of x. Whenever you think of a parabola and you make the argument of the derivative and all of that, you're usually thinking, I have my response variable and my controlling variable, and I'm asking when the response variable, the rate of change is 0 with respect to x, to the controlling variable. In this case, the controlling variable is time. So the true graph that you should make is a graph that looks like this. Y as a function of time, and this one, coincidentally, will look like this. Oops. But that is because x is a linear function in time. So x and t with respect to this type of plots are indistinguishable. I just wanted to caution yourself with respect to that. Gracie, you follow? Okay. And Casey, I will trust that if you're not following you. So basically we have our equation for y dot as a function of time, and I want to ask myself to what time this is equal to 0. My equation is minus gt plus v0y. And then from here, you come up that v0y over g is equal to that time, which is equal to square root of 2 over 2, 114.14, all of this divided by 10. And this is equal to square root of 2 over 2, 1.414. And I was saying that this was basically approximating it by square root of 2. So this is around 1 second. Time that it takes the particle to go there. Make sense? Cool. What about when the particle reaches here? Now what? What do we do? I plug in y not equals 0. Sorry, no can do because this is fixed to this age. Keep trying. I cannot change why not. Why not? I already solved the differential equation. Oh, I do have, yeah, I do have a function that tells me where the particle is at every time. So I just need to ask for what time that is equal to 0. Very good. So I don't think, I just come in here. We bring this equation here. And I say, for when time this is equal to 0. And we solve. So I have 0 is equal to minus gt squared over 2 plus v0 yt plus y0. And t is equal to plus minus v naught. No, what am I doing? Is equal to minus v naught plus minus the square root of v naught squared y plus 4 g over 2 y naught divided by minus 2 g over 2. I did this right? Yep. Why do I have two solutions? Your system doesn't know it. We threw this particle by yourselves, but if you were to do an analytic continuation of this trajectory, you will get something that touches here. So if this, you have to remember that this is valid description between t equals 0 and some maximum thing where the thing hits the floor, and after that I stop the simulation because I'm not going to be able to track that the thing went past to the floor. But the math doesn't know that. So that's why you end up following one equation. The rest is just numbers. You can figure out the final numerical value for when the particle hits the ground. Does this make sense? Were you able to follow all the steps? Can one of you summarize for me what did we do? I'm going to even hide it. What were the steps that we followed for this problem?
The first step was that we found the
Mm-hmm. Which were?
the motion.
Perfect. The position.
Yes.
But perfect, yes.
Yes.
Mm-hmm. That's very good. You're doing great.
And then we figured out what.
Mm-hmm.
And we started with force, the time derivative.
Mm-hmm.
And then from there, developed equations separately in X and Y.
Mm-hmm.
And then we were able to then
Once you solve the equation, you're God, because you have everything that there is to know about the system as a function of time. And then any question that anybody asks you, you just plug it in there. You have the functions, so you find it. Yes? Thank you, Chris. That is a fantastic summary. Everybody happy? All right. Let's talk about conservation of energy and how we will solve this problem, or parts of this problem, using conservation of energy. I actually don't think, I need to think to make sure that what I'm about to say is right, but I'm almost sure that you cannot obtain, unless you play a lot, what is this time from just playing with the conservation of energy. But the height is going to be very easy to solve. So the idea in here is that on most, if not all, how do I explain this in a way that I don't say lies, but at the same time I'm saying something that is useful? All right, let's take this analogy with the money in a more serious way. Except when you have very weird situations in the world happening. I don't know if you saw the Batman movie, the Christopher Nolan ones. There is this very famous one with Heath Ledger. He's a Joker, and at some point he gets all this money that he obtains from all these mobs and bad people, and he burns it, because why not? He was. So when you do that, the money literally disappeared. The money didn't go from one person to another. It doesn't exist anymore. I have no idea what the banks are going to do to account for that. Unless you have something like that, in everyday interactions that you have with people, money is conserved. Sometimes the government prints more money, but that's another issue. So if you buy something in the store, you're giving the person in the store that amount of money. Now you have the object. Now it's their turn to spend that money into something else. In most physical processes, if not all of them that we know, the particles interact, the systems interact in such a way that energy is conserved. So the only thing that happens is an exchange of energy. One particle will change parts of its potential energy to a kinetic energy and vice versa. Two particles will collide and they will exchange momentum and energy and so forth. Yet, because as humans, we really want to avoid having to track every single degree of freedom of your particles. And by that I mean, when I throw the ball, I'm not throwing a ball. I'm throwing 10 to the 24 atoms that somehow are glued together in a very weird way. They're traveling to space, colliding with air. The air is full of other 10 to the many big number of atoms. So it's a very complicated process. And if I really wanted to explain it in that way, there's probably not enough atoms in the universe for me to even write down the equations of motions that will entail. So as humans, we decide to make sacrifice. We decide to simplify our system and describe it in less amount of degrees of freedom that I actually will need to fully understand what is happening. Does that make sense so far? That's where friction comes in, and these non-reversible processes. It's not that the thing is non-reversible. It's not that the energy got lost. It's that the energy was sent to degrees of freedom that you are not taking into account in your description. Because we want to account for that without having to explicitly count them, we made up these concepts, which is a very good model. It's a very good idea of the world. It's saying, by the way, my ball is going to be moving. I'm going to shoot it with a certain energy, and almost perfect approximation is going to land with the same energy. I guarantee you, it's going to be a little bit less. Why? Well, because some of it was lost in degrees of freedom that are not taken into account. I'm going to call that friction, and I'm going to model it in that way. Oh, look, it works very nice. But now your equations of motions break the symmetry or the property that energy is conserved. You just have to take it into account in a different way. Make sense? So the equation that I'm going to write is that the energy at the final stage of any dynamical process that your system is going through minus the energy at the initial stage out of the process that we're about to hit play in time and look at, is going to be equal to the work done by non-conservative processes, aka friction or heat, that will appear later whenever, if at some point we talk about thermodynamics. Yep. In principle, this should be a very nice and juicy zero, and it is. But because we cannot take into account all the degrees of freedom, we treat it as the work done by non-conservative process. Let me close this, otherwise I'm going to get distracted. Okay, in the process that we're talking about, we have kinetic energies, which for my particle is going to be equal to 1/2 the mass of the particle and the velocity of the particle at that time. And look at what I'm going to do. I'm going to put in here a time to remind us that these are not numbers, these are function of time. I can ask, what is the kinetic energy at this specific moment in my process? Yep. And then I have a potential energy. How do we call potential energy? B. Also as a function of time. That in this case is going to be equal to mgh as a function of time, which, funny enough, we do have a quantity that we were calling like that, which is the position in y as a function of time of the particle. This v is, of course, going to be equal to x dot square as a function of time plus y dot square. And if we are neglecting air, then that is equivalent to saying no friction, therefore energy at the end has to be equal to energy at the beginning. Yep. So let's calculate that. This is my initial situation. How much is the energy at the beginning? And this is how you do this. The same as I have been telling you of recipes to have a direct trigger of thought that then is followed by more elaborate thought. You say, okay, E kinetic initial plus E potential initial. Am I missing anybody else? Did we have any other source of energy in this thing? No? Okay, so that's it. And then we're going to plug numbers for this. Make sense? So how much was the kinetic energy at the beginning? We said that V0 was 14.14 meters per second. That was magnitude. We said that the mass of the particle was equal to 0.1 kilograms. We said that the height was equal to 10 meters. And we said that G was equal to 10 meters per second square. How much is my energy? Now I need help from you all. More than a number, I want the process of constructing the number. So what do I do in here? What do I plug?
For initial kinetic energy, we just have whatever the mass is that's given, and then our velocity as a function of time is just our entire starting velocity. So we don't necessarily have to worry about splitting it into x and y components just yet.
So my velocity as a function of time, I'm evaluating at t equals 0. Right. So I just need the magnitude of the speed or the velocity at that location, which is 14.14 square. So 14.14 square. Yep. Which, and then I'm not missing anybody else. Alex pointed out that this is square root of 2 multiplied by 10. So this is equal to 1/2, 0.1, 10 square, square root of 2 square, which is a 2. So these two cancels. This square cancels with this one, and this is a total of 10 joules, which is exactly what I wanted. Yep. What about the potential energy at the beginning? Mm-hmm.
The height at that point, which is 8.1.
So So 10 joules as well. Nice, good numbers. It's almost as if somebody thought of what to put in these numbers to make it relatively round up. What will be the end? The end of what? The end of time is the apocalypse. What do I put in here?
Find the height, or are we trying to find?
I'm trying to find the height, the maximum height that this thing entails.
We do the same thing, but instead of the velocity in the full magnitude originally, the velocity, the y component of velocity is 0, and the x component hasn't changed.
Before you go in that direction, I just wanted to point out the trajectory does this. My end is here because I want to find the maximum height in there. Yeah, so now E kinetic final, you were saying that this is going to be 1/2 m vx squared plus vy squared, and you made the point, well, at that point, that's the whole point of this thing, this is 0, right? So I'm going to have how much in total kinetic energy that I had before? So if before I had 10 joules made out of these two components that were symmetric because I had 45 degrees, how much do I have right now? Just half of that, right? By symmetry. You can make the calculation again, but do you see it? I'm going to have 5 joules. Because at the very beginning, it was symmetric. I was shooting some speed in x, the same speed in y, and that total gave me 10. I now have completely killed the speed in y. I have half of what I had. Casey, you with us?
Yes, sorry.
Excellent. No, don't be sorry. All good. Okay, so I ask you all, what is the potential energy final? Without making any complicated calculation, how much should this be? 15. How? How do you know?
The total energy.
The total energy is conserved. So you see in here, if I, beforehand, I had 20, and I had 20 because I had this 10, and I had this 10, and now I have 5 on this, well, those 5 better be somewhere else. Where else but on the height? So then I ask you, if a height of 10 meters gave me 10 joules, how much height do I need, given that height is linear in this equation, to obtain 15 joules?
Hopefully 15.
That's it. And that's the solution. And we're done. You see how easy? That's how you use conservation of energy to solve this type of. If you want to answer questions about the dynamics, at what time the particle, it's a bit more complicated. You probably need to fully obtain the equations of motions of these things. But there's many questions that can be answered super quickly if you think in this way in terms of the conservation of energy. Make sense? Final question. What is the kinetic energy of the particle once it's down here? I could have asked that as well on the previous one, but I want to ask you now. How would you figure that one out?
The bottom, we would have y equals 0.
Mhm.
We have no potential. All of it would have.
So how much is your total kinetic energy? That's it. You want to figure out your speed? Just plug into the equation. You find the how much is x and how much is y. That's we'll have to think a bit more. How is that distributed in x and y? One way of thinking is the magnitude in x never changes, so that is fixed. So then you can figure out what is the y contribution to the energy that will give me the 20 joules in this thing. And that probably should be 15 joules. Makes sense? Okay, so what we're going to do, time has been passing way faster than I thought. We are going to take a 4-minute break. After we come back, we are going to quickly play the Monopoly game and see if it's fun or not for this example, and then we're going to do the other 3 examples as quickly as we can, because next class I would like to start talking about Lagranges. So, with that, I will see you at 2:24 minutes, 2:27, 2:28, so you have a bit more. All right, so I'm going to give you a bunch of energy bills. I'm going to have, since it's only the 4 of us, you're going to have to serve both as stations, as the bank of energy, and as a particle. And I knew that I should have brought something for the particle, so for now, the particle is going to be a cup of freezes. None of you are allergic. Okay. For this problem, this is going to sound silly because we already solved it, but we're going to start with you. You're going to have the particle. What did we say at the very beginning that the particle is sitting with Alex in station A? How much did we say that it had for the energies? Do you remember? 10 and 10. So can you grab 10 of the bills? I need you to have 10 joules of kinetic energy and 10 joules of potential energy. So I'm going to label them, let's say, 10 joules of kinetic energy and plus 10 joules of potential energy. Yeah, and that is where the recess is sitting. Now it moves to station B. And then what happens? Can you take the recess, Grace? So once it moves to station B, it's going to go up in height. That means that it's going to gain some potential energy, but it has to come at the expense of some of its kinetic energy. So what will happen out of the 10 joules that you have in kinetic energy? What are you going to do with those? Right? You're going to grab 5 that you have in here. Now we know perfect. Now we know the conversion rates, and it costs 5 joules to go from this point to this point in terms of potential energy. So now what is your new distribution? You have 5 joules of kinetic energy, and you have 15 joules of potential energy, which is equal to 20 joules of total energy because energy is conserved, right? And now you're going to give the particle to Cooper. When the particle goes all the way in here, what happens to its potential energy? You have no potential energy. So then you, my friend, how much kinetic energy you're going to have? You're going to have 20 joules. Kinetic energy plus 0. Which is equal to 20. Yeah? Does that make sense? Excellent, fantastic. Can you show the camera your 20? Oh, what are you going to do with so much joules money? Makes sense, right? Okay, let's try to solve now the next problem. And you can, so put all the money in the bank. You're still going to have 3 stations. My second problem is a problem with a spring. So what I have, if a particle I have more. You can eat it. I have more. Can you catch? No, the particle. Okay, go pick up the particle. So the next problem I have mass 0.1. This has what did I put for the constant of the spring? What did I say? I did work out these numbers so that things will make sense. And if we cannot finish this today, I think that's completely fine. We can continue discussing it more. So, but I think I would like to at least go through some of the ideas of the energy conservation. So here the K is 200 newtons per meter, and my initial position is equal to 0.224, and I start with an initial speed of square root of 2 times 10, as we have discussed before. Yep. Okay. So the 3 locations that are, what is this spring going to do? If I start time at t equals 0 with my mass, it's displaced already by some amount, and it has some initial speed to the right. Can you tell me what is the movement that is going to happen in here? Intuitively. It's going to oscillate, but as soon as time starts passing, the thing is going to start moving to the right going to reach a maximum amplitude, and then it's going to come, pass through the center, and then come to the other side, and then oscillate. Yeah. The new concept that probably you have seen in your undergrad, but that's why I'm here to talk about these things. The new type of energy that we need to talk about is how a spring accumulates potential energy. How can I come up with a model that tells me, based on how contracted or elongated it is, the amount of energy that is stored? And that, the potential energy in here is going to be equal to 1/2 K delta X squared, where delta X is a deviation from the equilibrium position. Now, I'm going to assume that this is X as a function of time, and the equilibrium position is 0, so I can call this just X squared. Yep. Any questions with respect to this? Okay. Oh, because I'm not letting it go in the equilibrium position.
No, I know. But you're saying the equilibrium is just really like.
Yes.
I mean, like it's like half the wall.
Ah, this thing can oscillate between. This is going to be doing this. That's not a wall. Yeah. Yeah. It's a magical wall. Yeah. It's a wall, but the thing passes through. A very, very good question. Does that make sense? I just grab it. I don't know. I have a magical pin, and the thing oscillates back and forth between these two things. Yep. Okay. You don't have a problem with my wall. So the three stages that I want to calculate with you are here when the thing is about to start going. So this is A. Then the point B is going to be the maximum amplitude that this is going to have. And then point C is when it's coming back. And it's passing, colliding with the magical wall and going through the other part of that magical wall. Make sense? So before we actually go into the differential equation, I want to calculate with you the energy distribution of these things. So how much is the total energy in A with, once again, this is you, Alex. So how much is this going to be? First easiest thing. The total energy is kinetic energy plus potential. So that's the first thing we write. EK plus EV. All right, so how much is your kinetic energy? K, why K?
Oh, kinetic energy. And
Okay, how much is that? So if is this square, that is 2 times 10 squared, and then that is multiplied by the 1/2, and that is multiplied by the 0.1. 10 joules. Once again, can you grab 10 joules from the bank of energy for you? Thank you. Yes, from the kinetic energy. Very good. Okay, how about the potential energy? How much is the potential energy in that location? Now is 1/2 kx squared. And how much is this? So it's equal to 1/2 k 200 joules per meter Something is wrong. I think it's newtons per meter. Yep. Yes. It's newtons per meter, which is joules per meter square, right? Because newton is joules per meter times meter per meter. The final thing has to be meters in joules. So I think it's 200 joules per meter square. And then I have my x, which is this number, which I actually don't remember what this number is. Could this be square root of times this? No. I think, no, what is this number? Why this number? Why did I put this number? Well, you know what? We have a calculator somewhere. I hope that you have a calculator. So this is 0. Oh, I don't remember why I put this number, but that is a number that we put. So we're going to, yeah, 0.224 square. Can anybody with a phone, my phone is recording, make this calculation? Casey, this is a moment that you shine with your capabilities of being in front of a computer. How much is this? Why did I put this number?
0.05.
Sorry?
0.05.
It's a square root of 0.5. Okay.
Oh, so this whole thing is 0.5?
0.05.
Oh, 0.05?
Type that in. 0.224 times 1.224.
Okay, 0.
Since it'd be less.
0.05.
Okay, 0.05?
That
Okay,
makes it
that gets
5.
rid of. Perfect.
Yeah, okay. So, excellent, fantastic. So these two cancel these. I have 100, and this is 5 joules.
Perfect.
Oh, fantastic. That's why I put that number. Very good. Congratulations, Paz Pablo. Yep. So can you get 5 joules? Casey, do you agree? I'm going to assume yes.
Sorry, 1 second.
That's okay.
Probably though.
Probably, right? Sounds about right. Okay, so we're starting here with a total of 15 joules, 10 of which is kinetic energy and 5 of which is potential energy. Now we're going to move to point B. So can you move the resist particle? Yes, to point B. And I ask you, what is going to happen when you reach maximum amplitude? How much should the potential energy, sorry, the kinetic energy, be at point B? Why 0?
Because it's reached its maximum distance, so it's stopped.
So stop moving, it's about to start coming back. So this is 0. Oh, wait a minute. So then how much is the total potential energy?
And then it'll all go into potential.
Right? So it will be 15 joules. So if for any reason a maniac, when you enter today in the classroom, asks you how much is the maximum height, how do you find that out? You say this is going to be equal to 1/2 k x twiddle square, and you solve for what is x twiddle. What is the x that will give me this energy? We haven't even solved any differential equation. Yeah? You got it? Can you show the camera your nice 15 joules of potential energy? Wow, so much money. Make sense? Okay. What happens when the particles comes to point C? So eventually I should say this is B and now C. How much is the potential energy at point C? Do you have you need the resist? Yeah, that's okay, that's okay. Too much to take into account. So how much is that?
So now we'll have 0 joules of potential energy because we're at x equals 0.
Where is the magic wall, which means the spring is not complaining at all, which means you don't have any potential energy, but you still have to have your money. So what happened with your money? Excellent. EK is equal to 15 joules. Okay, this game is not terrible. I think I'm happy. I think I'm going to be doing this in the next iterations of the class, right?
I enjoy this.
Okay, fantastic. Yeah. Okay, good. Because we're going to keep doing it. But you see, now if somebody were to ask you what is the speed of the particle in there, that's it. You just write it. What would be the equivalent of Newton's approach to this? Well, you say, what is the first question we need to answer? Excellent. What is a good degree of freedom to describe what is happening to my system?
X.
And that's enough. I don't care about the color, y, no, there's no y. The rotation, no rotation. X as a function of time is all. So I write down here and I say, X as a function of time, who are you? What is my second step? I need an equation that tells me how X changes with respect to time, and that is equation of the forces. So I write the forces that are acting on my system. In this case, it's not a vector equation because it's one quantity. is going to be equal to m times x dot dot as a function of time. What are the forces that are acting on my system? Well, if the potential is this, the potential energy is this, remember that we talked about it, that forces are the minus gradient of the potential energy, because it's the thing that tries to point downhill. I don't have gradients because I don't have multivariate functions. I only have one, so the gradient becomes a derivative, the minus becomes a derivative with respect to x. So my force is equal to minus k times x. And would you look at that? This is the equation that I have to solve. I'm going to erase this m, and I'm going to put it in here. I have a function that I take two derivatives with respect to time, and I obtain the same function with a minus and a number. What is the solution to this? Sines and cosines, fantastic, yeah? Which one? Doesn't matter, the details come later, but the solution to this equation is sines and cosines. And you have to scream it with like 7 exclamation marks. Yep. And then you solve. Okay. The solution of this is going to be equal to, by the way, the frequency is going to be square root of k over m, which we already knew that from the first or the second class when we were talking about differential equations. So you write this as a times cosine of omega t plus b times sine of omega t. These a and b are not the same a and b as before. Don't get confused with that. And then you find what are the numbers a and b such that at t equals 0, my particle is here. And at t equals 0, the speed of the particle is this. You plug those in, you got the equation of motions as a function of time. You're done. Any questions that anybody wants to ask you, you got them. But see, we had to solve a differential equation, and now you have to deal with finding these two constants to then plug it in, to then try to find at what exact time the thing is turning back and blah, blah, blah. Answering the questions using conservation of energy was much more straightforward. Make sense? Okay, let's go to the next problem. Let's see how many we can do. We still have 10 more minutes. Okay. So probably the last problem that we're going to do today. Wow, we did a lot. I'm so happy. You have been an excellent crowd. It's this one. So what I have is basically a cone, like an absolute value function. It's not exactly like that, because if I leave this thing sharp, my particle cannot turn in. So imagine that magically, same as a magic wall, I'm able to make these two things and just connect it slightly a little bit with a tiny, we're not going to model that, but basically my particle is now doing this, comes up to some height, goes back, comes up, and it's going to be oscillating like that, with the caveat that there's a friction placing here. Now, what is friction? If you remember the discussion that we had an hour ago, friction is the dumpster in where you're going to throw away energy because you do not want to take into account those degrees of freedom. As my particle actually passes through the surface, it's going to have chemical interactions. It was going to lose electrons. It's going to reconfigure some of its molecules on the surface with the molecules of the surface of the other surface. It's a mess. I don't want to have to think of that. There's going to be heat. It's going to heat up. There's going to be phonons that are vibrating both in the surface and the particle. A mess. No, just friction. Yep. One way of modeling friction is to say that the friction force, the dynamic friction force, because you have the static one, which is what makes this thing not fall, well, then it falls. We usually model this friction force as proportional to a coefficient mu times the normal force that is being at place because of the surface. And if you think about it for a while, it makes sense. If you put your finger on the table and you drag it across, you feel some friction force. If you put more force into it, it's going to hurt and you're going to get more friction force. So it makes sense that it's proportional to the normal. This is under certain conditions, and of course, this doesn't work for sticky things like glue. And that's how we're going to model it. Now, this is the force. If I'm giving you a force, maybe I'm inviting you to solve a differential equation, but I'm going to argue that we can solve this problem. The question, which is, what is the maximum height after 2 oscillations, I think we can solve this without having to employ differential equations, but rather conservation of energy. Remember, we're going to take it into calculation. The final thing that you need to know is that the work done by any force is equal to the integral of the force times the displacement. So if you have an object, this is very content intuitive. It took me a long while to come to peace with this. If I'm lifting weights in the gym, the force, the energy, work is basically energy. The energy that I'm doing every time that I do this with my hand is going to be proportional to the force that I have to do to drag that thing times the displacement. If I were to just hold the weight in place, I'm applying a force, but I'm not making any displacement. According to this equation, there is no energy. Of course, there will be energy, and I will lose weight because of how the forces work in the human body is a mess. But mechanically, you will not be transferring energy to the other. Make sense by everybody? All right. So in this case, if my particle goes from this place to this place, the total amount of energy that is going to lose is going to be equal to that integral of the force times the displacement. The force, I'm going to assume that is mu times the normal. It doesn't depend on where I am, so it goes out of the integral, meaning the total thing in here is going to be force times the total displacement that I'm saying that is a length L. And the force, I think I said 60 degrees. So how much is the normal force acting in here? If this is mg, your normal force is going to be perpendicular to that. And it's just going to be the force that is responsible for making sure that your particle doesn't traverse through the surface. Alex, you with me? So this friend is going to be equal to mg cosine of theta. You can ask me more later if you want me to go through these things in more detail, but I do want to be able to finish this equation. So theta, I said that it was 60 degrees, so this is equal to mg times a half, which is cosine of 60. And the coefficient mu, I think I selected it to be 1. And once again, the mass is 0.1, gravity is 10, and length is 5 meters. So this entire thing is going to be equal to 0.1 times 10 for g times a half for the cosine times 5 because of the length. And this is equal to 5 halves, really? Okay. 5 halves of joules every time. Maybe I messed it up. Sorry? Is a 1 because I said mu equals to 1. So every time that I pass by, I lose 2.5 joules, which is terrible because that means we're going to have to break the money. But what can you do? We'll break. So my question that I want to answer is, the particle starts with some height, that in this case is 20 meters. And I want to do 2 full oscillations. That means, how much is the new height? So how are we going to do that? Well, we're going to assign labels. We're going to say, this is A, this is B, this is C, and then we're going to try to trace back what happens. So my question to you all, friends, and we start with Alex, because you're A, how much is the energy of my particle in A? 20 height, yep.
Still has a mass of 0.1. Then it starts with 20 joules of
Fantastic, 20 joules of potential energy. And how much of kinetic energy? Excellent. Yep, so get your money, let me know when you're ready. Good, so now, Grace, the particle is going to arrive at your station. How much potential energy you will get in your station?
I have 0 potential.
Potential energy is going to be 0 because it's at high 0. So all of it is going to be transformed into kinetic energy minus the amount that we had to throw into the unaccounted degrees of freedom, the government in this case, the taxes. How much do you throw away? Which is 2.5. So 2.5 joules went to friction. How much do you have left? If you have to break it, you have to break it. Excellent. So you have as kinetic energy 17.5 joules. You have my permission to break one of the things. Yep. Hi, Casey. Bye, Casey.
Bye.
Okay, okay. So this is how much you have. So what about Cooper? In C, how much kinetic energy you have, Cooper?
So I'll be back to, I'm assuming we're at the turning point, so we'll have 0.
You have 0 kinetic energy. How much is your potential energy?
So I'll have all 17.5 joules.
Okie dokie. Do you have your 17.5 joules? Yeah.
They are in stacks of 5,
Oh,
not less.
that would have been helpful.
Great, too. Everyone's name doesn't match their letter.
I noticed that as soon as you said that. A 9, 10, 11.
You also have my permission to break one of the. Yep.
Good, thank you. 17.5.
Aha, very good. So now, yeah, good thing that So now, here you go D. Here you go E, and we're only going to do these ones. So we're going to count how much there is at the end, because we are out of time, and I want to be respectful of that. So now we are at point D, which is the same point, but things are changing. So Grace, tell me, point D, how much is your potential energy? Excellent. How much is your kinetic energy? Oh, good. So do you have your, can you show to the camera your 17.5? And where is a half? There is a half. Perfect. Okay, and now we go to E. Alex, how much kinetic energy you have? And how much will be your potential energy? 15. Excellent. Why 15? Well, when the thing goes up, loses the same amount of joules. We are assuming that this friction force is independent on speed, which is a very good approximation for low speed and not viscous things. You lose 2.5 again, and you end up with 15. If we wanted to figure out how much is the height that you end up with, how much will that be? 15 meters. Can you extrapolate on how much will be the height after the second thingy? Easy peasy, no differential equation. If you had to solve a differential equation for this, well, you know how to do it. You write Newton's equations of motion, integrate, you have a constant force, you know what to do with that, and that's all. So for next class, the problem that I would like to tackle will be this one here that has a hoop. We're going to start with a mass, we let it go, some energy is lost in here, it goes through the hoop. We're going to have to think how much energy we have to shoot it such that when it goes through the hoop, it's able to have enough speed to go through it. And then it's going to come and compress a spring. And we're going to ask ourselves the questions, if I shoot this particle from the minimum height that I could so that it goes through the hoop, how much is going to compress the spring? And now you're experts. We're going to play basically the same game. You're going to figure out the amount of compression that happens in the spring is going to be related to the amount of energy that the particle arrives with it through the energy of the spring, and that's all. Very easy. Make sense? Cool. Any questions before we close? Okay, well, I wish you a fantastic rest of your days. I will see you on Wednesday for quantum mechanics. And thank you for playing with me. This was super fun.